Thank you, Simon, for the nice introduction. Hello, everyone. Yeah, as you can see from my title, today I will talk about the perovskite-based tandem solar cells and how we overcome the challenges for these devices, and with the spectroscopy perspective, let's say. Oops. Okay. So for the single junction solar cells, for instance, as a silicon that we can cover the spectrum up to some point, but for the photovoltaic devices, what we are looking for is the lower levelized cost of electricity, where the silicon is getting to its practical limits, that how we can reduce this as NGSE is basically combining it with another semiconductor that most of you know that the perovskites are like a quite nice top cells for these applications, and thanks to their tunable band gap, we can engineer their composition, and then we can apply this top cells as a bottom cell also, or for the other PV technologies. Therefore, we can use the solar spectrum more effectively. And I like this, actually, these AMOLF graphs that shows how you can really push the limit of these different technologies towards the detailed balance limit. Basically, it is going with the carrier management and also the light management. And you can see that this perovskite tandems, perovskite silicon tandems, or perovskite organic tandems, they are just lying around here. And while with this perovskite silicon tandem, last year was like an interesting year, that now we have the efficiency is more than 33%. But, and maybe most of you know that in the tandem field, let's say the perovskite silicon tandem field, that in our lab, our approach in KPV lab, our approach is the solution processed perovskite thin films on the textured surfaces. And in 2020, actually, there was a nice paper from the group that they managed to spin coat the perovskite on the textured silicon wafers that allows the full coverage of the perovskite on the film, basically reducing the pyramid size, tuning the pyramid of the silicon, that you can still benefit from the silicon's response, and also the adjusting the recombination junction and the film thickness. So is it only limited with the one step? Actually, no. I also adopt the two-step processing of the perovskite on top of these textured layers. For sure, our group is not limited with the solution processing, but why I wanted to show this, because the focus of this talk will be the solution process perovskites. So the perovskites are quite nice materials. They are working quite well in the TIF, in the single junction or the tandems, but still, if we are talking about semiconductors, I mean, we are also dealing with some recombination. So after the generation of the three carriers, what we are expecting, actually, the radiative recombination, because of the transition from a valence band to the conduction band to the valence band. This is the natural way to do it. But if we have some trap states, that these carriers, the generated carriers, will be trapped, that will leads to a non-radiative recombination that we don't want in the solar cells. Basically, it is lowering the quasi-from levels and reducing the effective charge densities. Therefore, that you are getting really, you are lowering the open circuit voltage in the device at the end. But how we can probe these losses, or how we can deal with the voltage losses, basically now the optical spectroscopy comes in, and it helps a lot. For sure, we are doing different spectroscopy techniques, but what you will see mostly today is it will be the imaging of the photoluminescence, and then the calculated physical meaning, calculated things out of it. So what are those? Basically, I will talk about this one. So, and also I will show you some examples. So here, to get the image of the sample, I mean, on a thin film on the surface, we are using the hyperspectral microscope. Basically, it gives the spectral and also the spatial information, because you are getting like a image that has the information from the from the 400 nanometer to up to more than 1600 nanometer we can get, and also on the area. And we can do it in the absolute mode. That means that you can get the absolute photoluminescence emission and also the electroluminescence emission. And having this data cube at the end that you can see here, this whole data cube at the end, we have a home-built MATLAB code, and we can get the quasi-Farm level splitting or the Urban energy or the PL peak position shifts, for instance, after the light illumination. I mean, continuous light illumination. So how we are getting this quasi-Farm level splitting is basically like that. We are getting the PL spectrum, and using the Ruffel generalized Planck law for this direct transition, we are measuring the absolute PL, and we are extracting this quasi-Farm level splitting that gives you information about the potential open circuit voltage of your sample or device stack. I mean, whatever you have as a sample. And also from using this reciprocity relation from the low energy tail of that PL, that we can also get the Urban energy, which is also important parameter, especially if you are dealing with the new compositions. Now I will give you some examples while we are dealing with these interface losses. First of all, I want to show you that how we are dealing with the losses for the NIP tandem sources, but this time it will be the bifacial device. So the bifacial device is actually not only getting the direct light from sun, but also the scattered or the reflected lights from the backside of the device. That's basically that you don't have like a opaque device at the back, but you have the transparent. This is the backside of the device, and this is the front. So we have the same active areas for the both sides that you can collect the reflected light from the back. So for this one, we are now we don't need to have like in the current matching condition, so we can go to the narrower bandgap because we will have like a more light from the silicon side. So we can have the narrow bandgap. That's here. What I use is 1.55 eV. And it's the pure iodide system, so we don't need to think about the halide segregation. So how we are measuring these devices, basically, you have the full one sun condition from the top of the device, and we use different filters to mimic the reflected light from the back. To do this, as I mentioned in the beginning of the talk, to do this, how I did it, basically with the two-step process. So two-step process is the depositing of the lead iodide, again with the solution process on the textured silicon, then basically using the cation, organic cation in the IPA solution, that it's going through the lead iodide layer, then it forms the perovskite. But here you can see that when you look from the top, actually you might think that you have quite nice crystalline perovskite, but in reality that underneath you have excess of lead iodide, which is not converted. So how we are dealing with it, we tune the lead iodide thickness first, that you can cover all these silicon, the pyramids, then basically playing with the concentration on top of it, that you can have really nicely crystalline, fully converted perovskite. But as I mentioned, especially when we put some charge transport layers, that we might have some interfacial recombination. That's why we need to passivate the interfaces. Now here I use butylammonium-based cations, namely N-butylammonium or isobutylammonium for the top of the perovskite. But when you think about the regular device structure, we don't, the light is coming from here, so we don't really think about the high exton binding energy of the 2D perovskites, because for this larger cation, what we are expecting to have the lower dimensional perovskites. In this case, now we have a challenge from the light is coming from the top, and first it will see the 2D perovskite, which has the high exton binding energy. So in general, when you have a PL, you have the main peak of the 3D perovskite, and you have your passivation peaks. So for instance, when you get this plot, you may not know if you really have like a uniform formation of the 2D on the surface or not. So how we can see it, basically, I can show you as an example for n equals 2, around like a 570 nanometer, then you can get the image of using the hyperspectral microscope. You can get the image for the control. So yeah, we don't have any formation of the 2D. You don't see any extonic emissions here. But for the other samples, for instance, here, that you see the formations of these 2D, which is not that super uniform here. On the other hand, here that you have really strong extonic emissions. So, I mean, in this case, we don't care about this really uniform formation because this wasn't the PIN structure. So we don't care about really the exton binding energy. But in my case, for these N-butylammonium and isobutylammonium, the formation of these, it was important. And we basically checked again with the PL, as I mentioned, we need to get rid of, we need to deal with this high exton binding energy since the light is coming from the top. What we have is the non-uniform formation of these crystals. So you can see that some regions around like maybe let's say up to 1 micrometer, that you see the formation of these extonic peaks, while the rest is like a darker. And you see from this actually what it gives us an information, this PL maximum and minimum, is that on the surface, not on the whole film. So that's why you can easily see these formation of these extonic peaks. So, okay, we say that we have non-uniform formation of these 2D crystals. I mean, I didn't show it here, but in the GVAX also we can see that we have these crystals. Then I checked the time resolved PL, what we are getting actually. So again, you can see these extonic peaks and how they are decaying, while this is the perovskite. I mean, the main peak is forming. Basically, when we fit the time resolved PL decays, we're using the general rate equation, that you can see these. This is K1 corresponds to the Shockley Reed Hall rate constant. This is radiator rate constant. And again, using the absolute PL, that we can get the quasi-form level splitting as expected, since we are passivating the surface, that voltage output, potential voltage output is also increasing. So it seems like actually N-butylammonium or isobutylammonium, it doesn't matter, they are working quite, let's say, similar. They are giving quite nice results. But what about the device performance? Because N-butylammonium is slightly longer chain than the isobutylammonium. So to understand this, now we need to see the charge extraction or the interfacial recombination at that perovskite and the HDL interface, since we are using the NIP perovskite silicon tandem structure that you can see. Now the perovskite is contacting with the spiro TTP. So how we can check the after the generation of the free carriers, how will be the collection at that interface? So to do this, actually, basically, using the transient photoluminescence measurement used with the HDL stack, that you can excite at really low fluences, that you cannot getting the contribution from the second or the third order recombination, that from the differential lifetime, you can separate, or at least you can have an idea between the charge transfer or the interfacial recombination part. So basically the change from transfer to the interfacial recombination, that for instance in the isobutylammonium one, that it is reaching to the plateau, that gives you an information that you are passivating the interface compared to the control, and it is giving quite similar charge extraction with the control. On the other hand, the N-butylammonium shows a different behavior. It is getting really slowed down. So basically, slow down the charge extraction, let's say. So basically, what we can say here, the isobutylammonium is a shorter spacer than the N-butylammonium. Therefore, it reduced the charge accumulation at these thinner quantum wells, through the tunneling, and then via tunneling through the barrier induced by the spacer cation. So how at the end the performance was working? So for this one, actually, we can get higher current density compared to the control. So basically the n-butylammonium based one was not working well as in the isobutylammonium, and we get like a higher open circuit voltage as expected. So with the different rear side illumination, as I mentioned previously, that by changing the filter that you can mimic the reflected light, because the different backgrounds give different rear side illumination to your device. So we have like a quite nice sharp increase at the beginning. So as low as like a 16%, let's say, the rear illumination, you can reach to close to 23 milliamp per centimeter square for these devices. That gives the power generation density more than 27 millivolt per centimeter square. It's not only, this is not only helping with the performance, but also what we are expecting from these 2D perovskites, that the samples will be like more humidity resilient. So this is one of the nice things that you can see. Here is the samples optical microscope image, and you can see that the area 1 and area 2, they show different, different formation of these 2D. Let's say for the area 1 that you don't have too much 2D formation, but for the area 2 that you have quite a lot extonic peaks. And therefore, this is because of the parasitic absorption of the 2D, that you see darker for the PL peak position of the 3D perovskite. But after some time, when we keep these samples in like an ambient environment, so after like 8 days, that again, this average PL on this area for the with 2D one, actually it is higher than the without 2D one, which is, I think, the direct evidence of the degradation of the perovskite when you keep them in air after some time. For the PIN tandems, we know in the perovskite field that perovskite C60 interface is the problematic interface. So you can see from that how much voltage loss that we could have actually when we put the C60 on top of the perovskite, when we deposit C60 on top of it. So for last year, actually, we published a paper that shows that when you put a distance between the C60 and perovskite, that you are basically reducing this formation of these density of states within the bandgap. So we call it like a contact displacement approach. I think most of the people in the perovskite tandem field that they aware of it, that we need to really passivate that interface or put like a let's say lithium fluoride, magnesium fluoride, like a different metal fluorides. They are working quite well to make this contact displacement. So for our also PIN devices that we are using this approach, but also recently we have been working on this perovskite C60 interfaces. There was like a collaboration with the University of Toronto with the wider bandgap. So if you have like a more bromide in the perovskite structure, that you have more voltage deficit. So this is also what we are seeing in the 1.6 eV or 1.8 eV, 2 eV perovskites. So why this is happening? Actually, that maybe I need to first show here that how that on the surface of the perovskite you might have really, really low cosiform level splitting areas, like a really up to 0.9 volt electron volt areas that are really affecting the perovskite silicon, perovskite C60 interface. This is basically because of the it might be the band misalignment, it might be the energy level pinning, or the halide migration that's causing this effect. But how we can solve it actually to make the perovskite films, this is the potential map of the control and the PDIE treated one. So basically with these iodide bromide mixtures, they are just broadening the they fluctuate the potential at that interface. So using this PDIE, you are reducing the population of the minority carriers at that interface because this material is a short chain and a strong level space that is changing the surface energetics of the film. So what happened at the end when you do the PDIE treated one, actually, it is slightly becomes like a more homogeneous, let's say, but when you put the C60, that you will see really like a huge difference compared to the control one. So what we need to have this special homogeneous films also in the perovskite surface that will narrow this contact potential distribution, therefore reduce recombination at that interface. So this was the perovskite tandem that was helping a lot with the open circuit voltage for these devices, but also it is working in the perovskite silicon tandems that we have 1.68 EV perovskite. So for these ones, we were also working from the subcell analysis, as I mentioned, that we can do the electroluminescence measurements. So from the same spot of the device, we can selectively get the emission from the perovskite that you can see here, or the silicon. Actually, for this one, I need to shift a bit the silicon. Silicon is quite uniform. That's why I want to show that this is the silver finger part, that you don't have any emission. And from that you can, and also with the recent one, maybe that part I need to say that because it's the confidential, that we can really increase the perovskite top cell voltage. That is the different story. And with the different injection levels that you can mimic the JV for this perovskite. So this is the 32.5% device, tandem device that we have. And actually, we can get up to 84%. So the field factors, that means that if we don't have any serious resistance issues, that the potential of this device is actually quite high. And after that, so I need to, maybe I want to show like a really short explanation that how we are getting the higher current density. So this was just recently online, actually it's in the accelerated publication. Maybe it's like within 2 weeks, let's say. So what we were doing, basically that first we focus on the top part of the our tandem device, and we reduce the thickness of the TCU that we are using, and also the other stack. So you can see that here that we went to the up to 40 nanometer, we reduced the top TCO. That leads to really higher current densities, but we cannot now we have to also deal with the bottom part of the device, because when we are enhancing the top part, then we started to be we need to catch the current matching condition for those ones, because we were for sure getting higher current densities from the perovskite side. So for that one, for that one, basically what we did, this is the regular device at the backside of the device, and this is with the rear reflector. For that one, we are putting like a high refractive index material between the silver and the TCO at the back that we are using. And then we also tune its thickness to get rid of the parasitic absorptions, let's say. And you can see that we can get up to 20.9, close to 21 milliamps per centimeter square with the optimized devices. Before doing this, for sure, we did some optical analysis, and then with the using like some models that I'm not that really expert of it. But what we have at the end, with the help of the blue response in the perovskite side, and also the enhanced IR response from the silicon side, that we can get nearly 1 milliamp per centimeter square enhancement compared to our previous, let's say, devices, like a non-ideal, let's say, optical non-ideal ones. That this is the optimized and with the optimized one we are working on now. And also at the recombination junction part, we also use different recombination junction layers, and also we thin down those layers. And here the ISO gives like a quite uniform homogeneous potential again, compared to the ITO and ISRO, let's say, because ISRO and ITO have crystal planes that yield to a different surface potential, while the ISO gives like an amorphous structure. And from the XPS analysis, we also found that ISO surface accommodates more hydroxyl groups that will lead to better self-assembly monolayer, in this case 2-PAC-Z coverage, therefore the enhanced electric field. What will lead to, for the thinner, let's say the thinner ISO case, that lead to the and slightly enhanced open circuit voltage, which is like with also more reproducibility, and also the fill factor. So with the better coverage of the ISO. So before finishing my talk now, I can say that this is the device for the certified 32.5%. So basically we enhance the optical and also the electrical part of the device. So we were really playing with the top and the bottom part of the device. And now with the different, let's say with playing a bit more with the perovskite, now we can get like a more than 33%. So, but unfortunately, I cannot give that much detail for this one, but it's coming, let's say. And with this, I want to conclude now what we have with the better self-assembly monolayer coverage at the HTL interface. It's enhancing the electric field, therefore it is improving the whole collection efficiency. Therefore, we have a higher fill factor on the voltage, open circuit voltage. And from the optical enhancement with the thin ISO at the top and also the rear side, we can get higher JSC. And also with the special homogeneous, also the perovskite films, and also the, for sure, the dealing with the C60 interface, it's also enhancing the open circuit voltage of these devices. So thank you very much for your time, and I'm ready for the questions.